Well, it's time. Welcome back, everyone. We're now working through week number 6 of the 16-week semester. And for the big announcements today, all the exams have been graded. And if you took the exam in person, I have a hard copy to return back to you. If you took the exam on a testing center, possibly you're in the fully online section, then I just went to your ISU email address and directly emailed back a PDF of your graded exam. But even for people who took the class in person in the classroom, if I just didn't catch you today with your exam, feel free to just send me an email and I'm happy to scan it and send it directly to you so you can get it sooner rather than later. Before we get going, any questions that folks would like to discuss relative to exam one? I have the solutions posted here, and these are the basic summary statistics. I didn't want to put too much summary statistics in for the sake of protecting student privacy, but usually the maximum is reported, and I reported the average as well. But any questions that folks have on exam one that you'd like to discuss? Okay, well, as far as the exams go, we're going to have just 3 exams that go like this. A reminder, in case you forgot, it's been a while since the first day of class. Our final exam is going to be a take-home exam. It will be assigned on Thursday of this week to be due on Thursday of finals week. But as far as the rest of the exams go, it's pretty much going to be the same kind of style that you saw in exam one. They'll be purely conceptual questions. And when we get closer to this weekend right here, I'll be filling out the information review problems for the exam two, and we'll get that one finished off before we go off to spring break. So where we're at so far, we're going to work through chapter 14. This one's kind of, again, an introductory section. It really says it right in the name. But right after we hinted, chapter 15 is when the course really starts to heat up quite a bit. Chapter 15 suddenly feels very technical, even compared against chapter 13. It'll cool off a little bit once we hit chapter 17, and that's when we're going to be picking up statistical method after statistical method. Think of everything we do here as really just getting a feel for what is a confidence interval, what is a hypothesis test, how to interpret the output of those before we get going on the more sound procedures. Well, that's my spiel to start us off, and this is where we left off last time. Well, not last time. Well, yes, last time, a week ago today. We've found how to find the critical values, Z star, relative to central probability indicated as a confidence level. So in other words, if we have a level of confidence, say 95%, what we're really trying to do is capture between 2 critical numbers, negative Z star, positive Z star, that area right in the middle. It'll be based off this model right here, since all we're really doing is counting standard deviations. And this syntax tells us once and for all how to get the critical number relative to any confidence level C. Just plug it into that formula and you're well on your way. Don't forget though, you would need parentheses around the numerator when you go to type it in. After we discuss getting the critical value, here's the syntax written out in a slightly better way. We went to the full procedure. So this now has everything. If we want to come up with a confidence interval with confidence level C, first thing we do is find the critical number, give the value sigma, that's the shady part of this. We have to have known sigma, divide by the square root of the sample size, and we're all set. So part of these things come from the fact that by the central limit theorem, the sample mean itself is distributed normally. That's why we use the normal distribution to find the critical number Z star. The sample mean X bar is estimating mu. That's our unknown parameter that we describe. And standard deviation happens to be sigma over the square root of n. So that's where some of these parts are coming from. X bar is the point estimate. And this is the standard deviation. Z star just counts how many standard deviations do you need to extend around the sample mean to be at its targeted level of confidence C. What do we mean by level of confidence C? Maybe let's add just one more statement there. I think that this part is really hard to say exactly. Oftentimes when we go to do a confidence interval, we don't say there's a probability that mu is in that interval. Either is or it isn't. We don't have a probability for that whatsoever. What we do have a probability for is the entire method, which starts with identifying a simple random sample, selecting it, calculating the mean, putting together these things, then we could say the method that produces two values here would be, say, 95% successful if that's the confidence level C. So written this out, the confidence level C is, we could say the success rate or probability of success. Let's say the success rate. I think that's a good way to think about it. It is the success rate. Because it's a rate, it's also a probability of the procedure to produce, it's getting a little bit longer than I thought, to produce, let me fix that right here, an interval. Here's that interval. We pick up numbers A and B when we go to calculate this interval. The value A, the lower bounded interval, is just when we use minus up here. B is when we just use plus. So it has success rate of producing an interval that actually contains mu, that unknown parameter. But mu could be anywhere. Mu could be out here, for example. That could be where mu lands, and that means our method was unsuccessful. Mu could potentially be somewhere right here inside the interval. What's always inside the interval dead center is x bar, because we produce the entire interval symmetrically by adding or subtracting the same value around x bar. That places it in the middle. So mu could be right there inside it. That's a good outcome. That would be a success. Or, mu could be just way out there. It could be a wildly unsuccessful interval. Anything at all could happen. When we say confidence level C, it just means if we repeat this 100 times, we expect, if it's 95% confidence, 95 of all those different intervals will truly contain the unknown parameter. So it's a lot to come back to, but this is what the interval looks like. I wouldn't necessarily want to even put mu anywhere here because, again, it could be anywhere. Just a 95% chance it's in this region around x bar. Well, with all that said and done, our next job is to practice running through one of these intervals. And we'll do that here in example 3. But any questions or comments at the moment, folks? Okay, so that's our procedure for the interval. And here's our first real set of data in producing a confidence interval. This is kind of fun data that I've used quite a lot. One of the reasons I like these particular data is I had one student that was actually stationed in Fukushima around 2011 during a really nasty earthquake. Big, what was that? Typhoon came through and all sorts of bad things happened. It knocked out a set of nuclear reactors, despite how over-engineered they were. It was just a perfect storm. And there was a global effects. So this is what this problem is all about. What happened on the rest of the planet after that meltdown? So it starts off by talking about radioactive cesium. So the waste product of nuclear reactors, and there was a meltdown in 2011. This stuff leaked into the Pacific Ocean, unfortunately. And people were looking into this right away. A study examined the radioactive cesium tissue concentration in a random sample of 16 Pacific bluefin tuna. So here's our 16 observations below. From that statement, in case we need it, we'll record N as 16. The actual fish is that scientific name for the Pacific bluefin tuna. And these were captured off the coast of California. So we're talking essentially the opposite side of the Pacific Ocean to some degree. That's a big expanse from Japan to California. This is only 4 months after the nuclear reactor meltdown of 2011. And so we want to know, after 4 months of this stuff leaking into the ocean and fish essentially mixing around with their exposure of it, how radioactive were these Pacific bluefin tuna? So here's the fish that they captured. Well, not exactly. This is the radioactive cesium concentration of these fish they captured. The unit is in becquerels per kilogram of dry tissue. meaning once they captured the fish, they let them dry out, they desiccate them, and then they're looking at the ratio of how much of this is actually radioactive cesium within the actual fish itself per kilogram of the desiccated fish tissue. So these are the concentrations. I don't know enough about nuclear engineering or radioactivity to be concerned at all. They're just numbers to me. But then they go on to tell us this piece of information. Historically, the population mean radioactive cesium tissue concentration in bluefin tuna has been below 2 becquerels per kilogram. So before the nuclear reactor meltdown, it was always below 2, and now we're looking at these data. Now it's concerning, right? Some of these start to look pretty radioactive. Again, we shouldn't be too alarmed until we know exactly a little bit more about that unit and where the danger zone is. I don't know if this is going to set off a Geiger counter or be glowing fish necessarily, but it's significantly above 2 becquerels per kilogram. At least we know there is a real global effect going on. So the question of the problem says, do these data provide significant statistical evidence that the mean radioactive cesium tissue concentration is above 2 becquerels per kilogram? This is a good part to pause because when you look at the data, I think everyone would say, yes, all the observations, every single one of them is way above 2 becquerels per kilogram. So why in the world would we even need to do statistics on this? The answer has got to be yes. It's not really a very middle of the road kind of problem. But the reason we do want to perform a statistical analysis is we'll surely answer this question, yes, but we're going to provide even more. The moment we calculate X bar is estimating mu. So we now have an estimate of the radioactivity of the population 4 months after. But then we'll produce the whole interval and we'll say, what are the all plausible values that mu could be with the confidence level that we'll determine. So we're not just answering the question here, we're giving more information. And that makes this a bona fide statistical problem for statistical inference. It says provide a complete analysis. And that just implies we're going to do these parts down below here. I print these out as well when we have homework assignments relative to a so-called complete analysis. And if you want a really fast rundown on what that entails, other than the outline that's right down here, take a look into assignment 5. Oh, no, don't take a look into that one. Take a look into the chapter we're in. I should have put that in the assignment. Chapter 14. And this is just a really fast write-up, trying to say, in essence, what are you doing whenever there's a complete analysis that we're meant to provide? Our author calls it the 4-step process. That just seems kind of weird to call it 4 steps. So I just rewrote it as being a complete analysis. So this gives us some ideas of what we're trying to do. In particular, this is the most important part, providing the conclusion. What we want is a practical one, which can be understood by a layperson, whether or not they've ever taken a statistics class or not. So we're trying to exclude special symbols. We'll never say mu is an element of that interval with probability 0.90. It's not even correct. It's the method has a probability of success. And this is kind of a nonsensical statement altogether. But more egregiously, we're trying to write out what this is all saying, as opposed to giving the symbols. That's the hard part about statistics. It's all about communicating the conclusion clearly. If we can't do that, it's as if this is really kind of good for nothing unless we can explain what we just did. Well, that's the whole problem. What we have to do first is state the practical question that requires statistical inference. This is something you can always state in your own words, but let's do this here now. If you just cite what the potential question is, the practical question is in the problem, then that's good enough for me as well. So this is a perfectly fine response. That's the practical question. Let's come down here and say, we want to address this. We're going to address it through a confidence interval, and that's always totally fine to answer it in that sort of way. Does that make sense to folks so far? Okay, I want to call this option 1 just to convey this is one way of doing it. The whole purpose of the state part is just so that I know that you know this is the main thrust of the question. Not worth a lot of credit. Usually it's just 1 point out of maybe a 12-point problem. But for another way of saying this, option two, option one is cite the question directly. And option two would just be put it in your own words. Okay, let's do just that. Any volunteers for saying what the practical question is in your own words? Kind of a tricky question, right? There's a lot of things you could say here. Yeah, go ahead.
Does the do these data show that there is a average radioactive tissue concentration in bluefin tuna that is above 2 becquerels per kilogram?
Yeah, I'd say that's terrific. So captures the essence of the practical question, and that would do the job. Let me get to, there's an average radioactive cesium tissue concentration. Let me know if I go off the track of what you said. That is above 2 becquerels per kilogram. So that would be a great way to say it. Thanks for the response on that one. And maybe another thing to add here, you don't necessarily have to write it in the form of a question. You could just say a statement that implies a question. You could say, we want to determine the radioactive cesium tissue concentration. You didn't say it as a question, but it implies one. The implication would be, well, what is the radioactive cesium tissue concentration? So again, if you just say a statement of what we're going to do, that's also totally fine with me as well. But that's the most confusing part in a certain sense, because there's a lot of things you can say. Just try to capture what the study is trying to do. Imagine you're in charge of that study. You're the head researcher, the head scientist, something like that. What is it you're trying to do? That kind of weird mental role playing sometimes helps out tremendously as well. But we're on to the next part then, the planning phase. The planning phase takes us all the way back to day one in the class. Defining the unknown parameter using the context is often pretty tricky in statistics, but we've been practicing that quite a bit since the very first day of the course. The unknown parameter would be, well, not X bar. That's something we know and we're going to calculate once we get further into the problem. Unknown parameter is mu, the thing we're trying to estimate in the very first place. We can say exactly what that is, then our conclusion is way easier to get to. So that's pretty much the purpose of this step right here, defining the parameter. We'll say mu equals. Now, first, we're saying mu because our data is quantitative. If our data was categorical, we'd use a whole different parameter. We'd be using p, the value that we saw, or parameter that we saw in chapter 13 for the very first time. We haven't done a lot of categorical data, so we'll wrap back into that parameter. For the while, it's going to be mu's in chapter 14, chapter 17, since it's just quantitative data. So because it's mu, well, what is mu? It is the population mean, and we have to say mean of a specific quantity. We can't go off to the rest of this and finish off the statement. So it's the mean of not these data, it's just the sample, but it gets us on the right track. If you're looking at quantitative data, and you put down parameter mu, take a look at the data again. That's the sample data, units of becquerels per kilogram of dry tissue. So we'll just say the mean radioactive cesium concentration not a bad idea to mention the unit. It's a weird one, so let's put it here. Becquerels per kilogram. And this ties in the fact that this is the radioactive cesium tissue concentration when we look at cesium per kilogram of dry tissue. So it's a population mean radioactive cesium concentration. We've mentioned what the data is. Now we have to mention what is the population. We'll say for all Pacific bluefin tuna. And here's where it gets tricky. We don't actually care about all of the Pacific bluefin tuna, but we're concerned about the geography element of this and the temporal element of this all at the same time. The geography element is we're concerned about the Pacific bluefin tuna that are around the coast of California. So we'll say nearby the coast of California, and we know that migrate a lot, but we're just concerned about the ones that are around that geographic location at that time, nearby the coast of California. And now here's where it gets even more tricky. Populations change with time. Every little event that happens on the planet can change the population. And some events are bigger than others, like nuclear reactor meltdowns. Those are earth-shattering events, essentially. So if we don't mention that this was specifically 4 months after the meltdown, we're not really capturing the essence of that population. It is a temporal statement that we have to put here as well. So we can say caught 4 months after the 2011 meltdown. There haven't been a lot of meltdowns, thankfully. So if you said the 2011 meltdown, everyone will know you're talking about Japan, the Fukushima reactor. So you don't necessarily have to say everything verbatim. If you can paraphrase a little bit, sometimes it's a good idea, because this is a complicated parameter already to indicate. But we got it, folks. If you're writing out your parameter and you're doing this for, say, a homework assignment, never hesitate to run it by me. I'm always happy to help out. Because I feel like this is a pretty hard part of statistics until we get really good practice on it. Well, we did this part. We've defined the unknown parameter. Next thing we have to do is determine a level of confidence for which we're going to estimate mu itself. Now, this is a weird part of the course because sometimes it's all up to you. Some of these problems are really kind of choose your own adventure. And that's what this is saying. It's up to you to decide. To an extent, we need to know what are the appropriate values of confidence and which ones would be really weird and we should avoid. So let's say that here is an overall statement. C less than equals 0.99, greater than equals 0.90 are typical. You would have to have a reason to be more than 0.99% confident. You can't be 100% confident. Your interval would be the entire real number line. And it would be extremely weird to be less than 90% confident. We'd have to have a really good reason for that as well. I'm not sure if I could come up with one. Higher level of confidence makes sense depending on how sensitive the problem is in the context. Maybe it's something medical, maybe something in engineering where errors could be devastating. We might want higher levels of confidence. But now it's up to you. Let's say we will estimate mu using C equals. I'll leave this one up to the class as well. Any volunteers for a level of confidence? 95 sounds great. Absolutely. Let's go with 95% confidence. So at 95% confidence, I think this is a typically nice middle of the road confidence level. If we go for a higher level of confidence, it means we require certainty, but it also makes our estimate much more wider. If we go too high in confidence, our interval could be so wide as to be not practical any longer. And going too low in confidence, well, it's going to give you a narrower interval, but now we have a 10% error rate in producing that interval. The method's going to fail 1 times out of 10. So we start to get uncomfortable going below that figure there. So good call on that one. We'll go with 95% confidence. Now we need to do some fast condition checking to see if we can use the procedure that was stated above. As far as the conditions are, we could look at them verbatim. One condition says the parameter mu is unknown, but you really wouldn't have to restate that. This is standard for any statistical inference problem. You wouldn't estimate mu if you knew mu. Another condition, however, is we have to have a simple random sample, and that's more serious, I would say. So the major things we want to check are randomization. We're looking back into the context of the problem to see if we know anything about how they selected those fish. I don't know how you would select a simple random sample of Pacific bluefin tuna, but if they have something that gave them a representative sample, not just all the fish that came off the first boat, then at least give us some indication of randomization. So let's go back to the problem and see just how they found them. Let's see. Random sample, 16 Pacific bluefin tuna. There's a sampling design there. Notice that they did not say simple random sample. So there's sometimes really complicated sampling designs that give us random data or representative data. Then knowing that we at least have a random sample is encouraging, so we'll say it down here. As far as randomization goes, we have a random sample. And so this condition is met. However, I think a lot of people in class might be slightly uncomfortable just saying, oh, it's met. They said they had a random sample. Because if you're looking at our procedures really carefully, you've noticed the central limit theorem says specifically simple random sample. Our procedures say select specifically a simple random sample as well. We don't know how they got this random sample. It could have been a very complicated design. And if we're worried about that, that's something we'll bring up in our conclusion down here. When we go to give a conclusion, we also mention anything that was a potential shortcoming. So in other words, I don't know for sure if this is a simple random sample. They didn't say so or not. So when I go to give a conclusion, if this really bothers me, I ought to say, however, my results could be challenged if the sample was not a simple random sample. We're using the wrong procedure to target the sampling design, in other words. You know what, let's say it down here, just in case I don't forget. We're going to give a conclusion somewhere here, but here's our catch-all statement. However, these conclusions may be challenged if the sampling design was not a simple random sample. And I think we've hinted at this before. Sometimes it gets even worse. A lot of times when you're looking into medical data and you're looking at, say, a very rare condition, it may be next to impossible to get a simple random sample. The researchers instead argue our sample is representative of everyone that has that condition. Now they are working extra hard, and those conclusions can be challenged if anything goes wrong, if there was true bias in their sampling. So that's always the most important condition there. We check for randomization. And I would say that this is something I wouldn't be too concerned if they just say random samples somewhere in the problem. Well, we have another condition to check. But any questions at the moment? Okay, we're almost to the fun part where we actually use the formula we've been looking at. But you notice in statistics, sometimes it's just a lot of writing, putting your thoughts together before you even get to that finish line. And what are the other conditions? Well, we had to have mu unknown. We have to have sigma actually known. So let's go check in our problem. Did they give us a value of sigma? Provide a complete analysis, assume that the population standard deviation is 2 becquerels per kilogram. I didn't even read that statement the first time. I think I just stopped on complete analysis. They did give us a sigma value. This is the part of the problem that's shady, that deserves chapter 17 to make a correction here. Because you have to wonder, if there was a meltdown severe enough to change the value of mu, making it above 2 becquerels per kilogram, why couldn't it change the value of sigma? That probably would go up, I would assume, more variable. But we're going to assume it's still 2.95 becquerels per kilogram. Historically, this is about what people did in the past, except they didn't use a value that they called sigma. They took the standard deviation of the whole sample and just plugged it in right here. They're using the sample standard deviation in this spot. That's not good in the sense that S, that's the sample standard deviation, is only approximately equal to the sigma population standard deviation. So that was estimates on top of estimates, and the work got very unstable on low samples. So we'll find out how to make this correction more concrete. But for the moment, we'll just work with that. We have sigma equals 2.95 becquerels per kilogram given. So those are the 2 conditions that we need so far. And the last condition, we're checking for normality of the data or deviations from normality. So condition 3, check for deviations from normality with the sample data. So what are we doing here on condition 3? Well, you might have noticed at the very top of the notes, simple inferences for the mean. We are assuming that the population itself is distributed normally. Now that's probably not true at all, but we wonder how untrue can it be? If we look at the sample data and that sample data is highly skewed, we have evidence the underlying population itself was potentially skewed. If we look at our sample data, we find that it's at least symmetric. Then it's a good call to use X bar in the first place to measure the center. And our procedure would tell us we haven't found any deviations from normality. We didn't find any violation on that simple condition for the population being normally distributed. So how do we check? Well, we go to the sample data, we're going to just throw it into a histogram and look at the shape of that data. Any questions at the moment before we jump into RStudio? Okay, so here's back to RStudio. This syntax was just getting critical numbers. We record it up there, higher up in the notes. First thing we need to do is import the data. It's been a little while, so just a quick reminder. Click this region here. First option, we'll pull up a file browser. My file is in chapter 14, example 3. It's also duplicated on Moodle. Then it's going to come in as becquerels per kilogram for that. That looks like it should be correct. So let's hit import. Now we've got data going this way. Let me fix my windows a little bit better here. Here's the 16 observations of the data frame. I'll close this. This is just visualizing it. I have a lot of these things. Okay, now we're ready to get started. So the data is right here. We can first extract it if you like, or just throw the whole data frame into the histogram function. I'll go this route. Let's go rad for radioactivity. Gets. Let me extend this a little bit better so we can see it. Example 3. So hit enter on that. $sign to go for becquerels per kilogram. And this should extract or one quantitative variable in that data frame. Next we'll hit histogram. Give it rad. This is a personal choice here. I'm deleting the main title, but some people have come up with really nice main titles for the histogram. If that's a process that you like, I'd say stick with it. This is just a stylistic choice more than anything. I'll give it an X label so we know what we're looking at. We just don't want just rad printed on the histogram. For example, if we run this syntax now, this is what we get. Not too illuminating. So let's say what we're really looking at. X label gets, let's see, radioactive cesium tissue concentration. This keeps on going. Let's see if we can fit this. Becquerels per kilogram mentions now the unit. And that really didn't fit too well, but there it is in one line. So that's probably how I would go for the histogram on this. Notice first, kind of a weird looking histogram at the moment. But let's run the syntax, see what we get. Click export here. Copy it to clipboard just to get a better visualization. And you know what kind of fits in there? If you ever have to summarize this a little bit better, I think just saying becquerels per kilogram would have been informative enough. The rest of the context of the entire problem would tell us, oh, we're just looking at the histogram of the data. But if you can make it a little bit more descriptive, sometimes it's well worth that small effort. Let me see if I can copy the plot with metafile selected. I usually just take a screenshot, but here it is. And we've got it. That's our display. So looking at that data, first question you might ask is it symmetric? If not, would you say it's skewed in one direction or the other? Kind of interesting as a gap here. Sometimes we call this bimodal data, since there seems to be a peak in this region, another big peak in this region. But you know, as far as symmetry goes, I would consider that to be the main peak. We try to fit a normal curve to it. It's not perfect data. We don't expect it. It's real scientific data, and it's messy, especially at small sample sizes. This is really not too bad in my view. So here we could say these data are roughly symmetric. If we were to say skewed, I would say probably skewed slightly to the left due to some observations here, but it's not a major skew enough to even mention. They're roughly symmetric. No outliers. None that we see just viewing on the histogram. And so from here, this does not prove the underlying population of all the fish, cesium tissue concentration, is really normally distributed, but it tells us it's plausible these data really could have come from a normal distribution. So let's say it here. It is plausible these data came from a normal distribution. So we can go on to say these conditions are met. We have some information on randomization. That's the shady condition there that requires chapter 17 to correct. And when we looked at the sample data, nothing told us the population itself had to be skewed. It could have been normal getting data like that. Well, let's put down some of the quick syntax that we used. Oh, let me try again. The syntax is here. But I was just to compute or produce the graphics. Well, any questions at the moment, folks, with the condition checking part of the problem? Okay, I want to expand a little bit more on what I'm saying here about it's plausible the data came from a normal distribution. There's a lot of different ways to look at that. Some people might have used a quantile plot. Our author discusses it in our textbook, but only as an optional side blurb, unfortunately. We're mainly just going to do it through visualizing the histograms. But if you're a fan of quantile plots, that's an acceptable way to go. You can't lose points in this class for knowing stuff. But to expand on this a little bit more, let me change out the syntax for something a little bit different. Let's just simulate what would happen if you select a sample of size 16, like in our problem, from a population that is exactly normally distributed? How bad do these histograms actually get? We can get a feel for that. Back over here, we could know, when is it implausible that they came from a normal distribution? How weird did it have to get? So let's say here, sample size n will be 16. And we're going to go to X. That's where the sample is going to live. So X gets. R means you're getting a random sample. Norm asserts it's coming from a normal distribution. 16 is just saying the sample size. And if I say nothing else, mean is 0, standard deviation is 1. Those values aren't as important. It's all about what is the shape that we see, less about where is it centered and how spread out. Next thing we'll do is just give a fast histogram of X. And this will show all the ways you can get a random sample of size 16. Well, not all the ways, but all the plausible ways of getting these kind of samples from an exactly normal distribution. Keep in mind that's pseudo-random numbers, but it does a pretty good job. So here's the first run. Pretty bad, right? If I solve this, this would be a procedure stopper. Significantly skewed to the left, potential outliers. Even if the population is normally distributed, we don't have a good read on X bar any longer. We would probably want to use the medium M to measure the center of these data. And if we knew nothing about the underlying population, looking at that would tell us it's plausible the population is distributed in a skewed way, not normal. Run it again, and you know what? That's not so bad. It has skew to the right, not as severe. Main peak is over here. Here, I would say this is pretty borderline, but a lot of people will call this very roughly symmetric, and we're all set. This doesn't violate the normality of the underlying population. Run it again, about the same, and these are the pictures we're starting to get, almost uniform on this. Pretty good on that one. That one is excellent. This is like winning a lottery ticket practically, if this was real scientific data. So the problem here is sample size is kind of low. If you went to 64, all these samples are going to start looking, or hang on, I was supposed to put an N here. So it updates when we update the sample size. Let's try it again. So if the sample size is 64, these are the samples we get. None of them are perfect, but you know what? They look a whole lot better than if it was sample size 16. A lot of those are pretty erratic. And if we're doing something like this, sample size 6, here's where we get some really big problems. At sample sizes of 6, we don't really have a good read on symmetry versus skew whatsoever any longer. There's not enough data to really give a whole shape anymore. What we're looking for is outliers that are too influential, that it's skewing X bar in one direction too far or another direction too far. And these samples, this one looks pretty good, but they're often going to look pretty weird like that. So again, we're pretty forgiving with the data that we see. It doesn't ever have to be perfect for us to say roughly symmetric. And this would be great, even though it does have this bimodal feature here and here. So this is the process of checking conditions. We'll do this a lot when we handle quantitative data. We'll always look into these kinds of conditions. But now we're on to the fun part of actually doing the computations. In order to get those computations out, first thing you'd want to probably do is just write down the formula we're about to use. It goes X bar, add or subtract our critical number Z star, and multiply it against sigma divided by the square root of n. And we have some of these values. N is stated to be 16. Sigma was stated to be 2.95. We're missing Z star, or are we? It was stated to be a confidence level of 95%. So Z is let me try again on that 95 immediately implies Z star, you could recalculate it, look at the table above. This is 1.9600 ran into 4 places. All that's left is X bar. We have to calculate it. The problem didn't tell us what X bar is. So we'll just go back to RStudio and get that value next. So back in let's go to this where we actually have the data. Only thing missing is mean of rad. So we now have the mean. This comes out to 10.3125. Let me try again on that. 3125. Now at this stage, we're just plugging it all in right here. You could use RStudio as just a way to put this in as a formula, then just run the script. But I think it's maybe a good idea to do some of these by hand occasionally, because this could be a real exam 2 question potentially, where sometimes we do fill out the formulas by hand, just as a concept check of knowing how to put it all together. Other times we'll use technology to make this all happen. But for the moment, think of this as being done as if it were an exam setting. Plug in X bar 10.3125. Add or subtract critical number we found to be 1.9600 last week. Multiply that by value for sigma, it's 2.95 up there on the statement of the problem. Divide by square root of sample size. There were 16 observations, so we're dividing by square root of 16 altogether. Let me double check my claim of 16 observations real fast here. Uh-oh, what'd I do? There it is. Yeah, 16 observations. So there's our formula. Now pretend this is just an ordinary calculator. Go 10.3125 minus 1.9600. Using this as a calculator, you do need to put a literal star here to indicate multiplication, or else RStudio is thinking you're calling a function when you're using parentheses in the ordinary way up here. Then 2.95 divide by square root 16, and that will give us our lower bound, 8.86. If you hit up arrow here, once, there you go. It calls the last computation, the last input you gave. So convert that to plus, and that's the whole interval. So we did it, folks. That's our first confidence interval. It has a small logical loophole that we have to correct. You assumed a value for sigma right here. And let's see how close that was. Standard deviation of rads is 2.8. We have a higher value here. In some sense, that's good. It's making our interval a little bit wider, capturing the uncertainty. We don't really know sigma whatsoever. We just threw in historical data, hoped for the best. But it is encouraging to see this value is at least a little bit larger than that one. Widens out our interval and makes our estimate more conservative in that sense. So there's the whole interval. It's totally fine to state your answer like this if you prefer, but I just put it in as a fast screenshot since I am terrible at remembering numbers when I'm tired. Usually I like to write out the interval like this. Therefore, the thing we want to estimate in the very first place, mu, we said what it was using words at the top of the notes, is now between let's call this maybe 8.9 and 11.8. I'll mention the unit to the right just once, becquerels per kilogram. So we've got it, folks. That's our confidence interval. Last thing we need to do is just give a practical interpretation. Any questions at all, folks, getting to this stage? Okay, when we go to interpret this interval, we just say what mu was, say what's between, and we do have to mention the confidence because the width of that interval highly depends on the confidence that you selected. So here's the write-up on one quick conclusion. This feels like it should be on the next page. We might say we have 95% confidence that, now we need to read out mu. See above for the guide on what we said it was, that the population mean radioactive cesium tissue concentration And we said it in a very precise way above. We said the Pacific bluefin tuna, but we can let some of that earlier context carry the weight for us. Let's say for these fish, that's referring to the Pacific bluefin tuna, and caught near the California coast. For 4 months. This is a really long parameter after the 2011 meltdown. Okay, so we have evidence that, or 95% confidence, that mean radioactive cesium tissue concentration, that's the becquerels per kilogram, is between 8.9 and 11.8 becquerels per kilogram. So that's the interpretation of the interval. But when we go to give a practical interpretation, sometimes we want a little bit more. It depends on what you said the practical question was at the very, very start of the problem, what you implied. The practical question might have been if you said, we're going to do this and didn't imply a question. So let's take a look at that and come back to this conclusion to see if we want to modify it. It's always a good idea to come back up here, double check your parameter, make sure we have everything that was important, then go all the way back to the top. And either way we said it, we have to make sure we really answered the question. So let's drop this back down just as a quick guide. So either way we looked at it, we were wondering if there's an average radioactive cesium tissue concentration, we're talking about the parameter value now, that is above 2 becquerels per kilogram. So for that practical question, what would you all say? Did we find that evidence or did we not find that evidence? So I'm shaking their heads yeses in the classroom. I agree with you all. You know, sometimes it's kind of tricky to say. Oh, sorry, question first.
It does show, data shows evidence for that cesium tissue concentration as the, with 95% confidence, we could say that the value, most of the values will be between 8.9 and 11.8, which are substantially higher than 2 becquerels per kilogram.
Exactly. And I like the way you said that because there's kind of a lot going on with this kind of picture. Let me try to capture that with a quick interval as well. Oh, hang on, what did I do here? Okay, I'll fix that later. I don't know how I did that. That was random. But if we put in just another view of what we've done, here's an interval that goes from 8.9 to 11.8. Dead center of that interval is x bar, but that's not what we're totally interested in. We're interested in the parameter mu itself. Now, way down the line on this interval, kind of hard to convey, so bear with me, is 2 becquerels per kilogram. And our parameter mu is within this interval with 95% confidence. So again, mu is most likely inside here. It could also be out there. It could also be way out there. We have no information to say exactly where it is until we sample all fish and then we've wiped out the Pacific bluefin tuna population entirely. But this is so far away from 2 becquerels per kilogram that we can say, yes, we really have found that significant statistical evidence, as you were saying. So there's no total certainty. That's the one thing we have to always admit in statistics. But there is the so-called significant statistical evidence. So let's say here, therefore, these data, because of the distance from 2 to the lower bound of the interval here, let's say these data provide overwhelmingly significant statistical evidence that I want to say the population mean. I'm referring to this whole statement right here. You don't have to say it twice. So let's just say that the population mean is above 2 becquerels per kilogram of dry tissue, just becquerels per kilogram for short. But keep in mind also, we didn't have great information on how the data was really even sampled. It would be really hard to assign a simple random sample to something like fish. They're so dynamic, you would have to say what every single member of the population is. I guess you could try to do that with billions of dollars and plant a chip on the fish. But now you're harming the population of fish. They're been traumatized just from that experience. Really no good way to try to get the actual simple random sample by identifying every member of the population. They had to have had a very complicated sampling design. So down here, we just mentioned, if there's something wrong in that sampling design, if people went back to the study and looked how they really got that fish, they might have found some biases in these data. That's where the challenge could be on our conclusion. So we should just mention it as a catch-all statement. I'm not too specific about this if you didn't say it in here. I'm not very picky. But whenever conditions are met, this is a good thing to think about. How can we protect our statement based off information we don't have access to? So just rewriting random there to fix that typo or the weird graphic glitch. Essentially, this is all about how confidence intervals go. What we'll do in chapter 17 is correct this procedure just a little bit. And if you're curious on how it goes, here's a massive preview to that. If we want to run a statistical procedure on the radians and do it in a way that's accurate, by accurate I mean when we say 95% confidence, we are really saying that statement correctly. We'll use a t-distribution and go t.test, rad, run this, and that's a more accurate confidence interval from 8.81 to 11.80. Now, notice it's a wider interval. It moves left this way, moves right this way, just a smidge. Let me check out my prior numbers. Kind of curious now. Prior numbers were from 8.867 up to 11.7, and now it's 11.8, 8.81. Yeah, we have a widening of our interval. And it is wider because when we go to use that procedure, this is in chapter 17, we'll look into this in a high level detail. We're not using that value. We have to admit it's an unknown. That means we're injecting uncertainty into the problem, and uncertainty just means a wider interval in practice. So that's the more accurate one in the sense that the 95% confidence is guaranteed to be more accurate here, but not here. We did our best we could with the information provided, but this is more likely flawed based on this statement right here. Any inaccuracies here are going to directly translate to a problem when we give a level of confidence. But what we'll take a look into next is just a couple of concepts, information about confidence intervals, and turn the problem over onto its head and look at it from the side of hypothesis testing. Any last questions at all, folks, before we go to the next example? Okay, here's that next example. There's several problems like this in the chapter 14 homework assignment. And I found that these are pretty tricky questions. So whenever you look into a problem in the homework that says, is this true or false based off what a friend might have said, for example, this is a good place to come back to. It says, suppose we have computed a 95% confidence interval. Here it is, represented as a mathematical interval from A to B for the parameter mu. You could rewrite this as mu between A and B. Really up to you. Some people like the mathematical interval form. Other people like the mathematical inequality form. I'd say whichever way looks best to you should be fine, but that's an A, not a 9. Let me fix that first. So first concept question asks, true or false? If we randomly select an individual from the population, there's a 95% chance that individual is inside the interval from A to B. How do folks feel about that one? Does that feel like it's true or does it feel like it's false? Turns out this one's false. It's kind of weird though. Something about this statement made it false, and it's not easy to pick out. It looks mostly true, absolutely, on face value. Anyone see the part of the statement that made it false? Yeah, go ahead.
Is it randomly selected individual or?
Yeah, it's really right here. This is what made it false. It's, again, kind of a trick question, right, in a certain sense. Let's explain why does it make it false in the first place, though? I mean, that's just as important, right? It's because this is the interval here. Mu is between A and B, but mu is not an individual. Mu is the average or the mean of the entire population. So the confidence interval isn't talking about single individuals in the sample, it's talking about everybody, the mean of everybody. So we can say here, false, since the interval describes mu, which is at the mean of the entire population. Now, part B is another false one. I feel like that one's just as surprising in a certain sense, depending on how you visualize this. This almost feels true. We've said a couple times, X bar is an AB. It's dead center. Anyone see what part makes this statement false here? It's not. Yeah, it's really the chance here. It feels right because we're talking about 95% confidence interval, right? But you're exactly right. When we go to form the confidence interval, the equation is this one. And this equation automatically implies X bar is dead center to every single confidence interval you ever calculate. What's unknown is where mu is relative to that confidence interval. That's the big question. So what made this statement false was, again, it's silly. Like you said, it should be 100% chance, not 95. So we'll say false. There is a 100% chance it is in the interval. We should be more specific because the extra information is that it's the exact center of the interval in the first place. It's the exact center. So I feel like these are tricky kind of concept questions. The rest of the questions are tricky too, but they can all be answered by just looking at the formula for the confidence interval. X bar plus or minus critical number Z star multiplied by a parameter that we are told we have a value for, divide by square root of sample size. So that's the whole interval. And now this is more of a mathematical question. If the sample size increases, that means this denominator gets bigger. What would you all say then? Does that widen or narrow the confidence interval? I agree with you, absolutely. The bigger n is, the bigger square root n gets, not as fast as we'd like, but it does get bigger. That means this whole quantity gets smaller, including the Z star because it's multiplying it. If this gets smaller, that's the margin of error. It determines the width. So we'll say it gets narrower. Let's say narrower since Z star times sigma over root n. So this is all about that n there gets smaller as n gets larger. So part C is our normal expectations. We expect a larger sample size to give us better information. And better information means a narrower confidence interval. The more narrower it gets, the smaller the margin of error, the more precise the estimate. And part D is where expectations go totally counter to what we want them to. Higher confidence is better, right? But we're saying decrease from a 95% confidence down to 90. That's a bad thing, but it gives us a good result. It narrows the confidence interval, unfortunately. So why is that? If the confidence decreases, Z star itself decreases. And we can see this. We produced a table. Let's take a look. We worked hard on this table. As the confidence decreases, Z star decreases as well. The decrease of Z star means this whole thing right here is going to get smaller and smaller as you become less confident. Well, it makes sense in a certain sense, right? The narrower interval means bigger chance for mu to be outside of it. You should be less confident. But the conflict here is when we see a narrow interval, we think, oh, precise estimate. Not the case. This is the reason you always have to report confidence, because if I misreport confidence, even on just the last question right here, I could give an interval that goes from barely over here to barely over here, make everyone think we have this fantastic estimate based off just 16 fish, but maybe the confidence was just 15%. That would be the part that made this whole thing kind of a big lie out of nowhere. So we must always report confidence. And this is the problem here. As C gets lower, so does this part right here. So does Z star. So lower confidence implies a narrower interval. So that's what's going on in part D. Again, this is kind of counter to our expectations. We have to really watch out for this one. If the confidence level decreases, we get a narrower interval. And the slightly dangerous looking color here is just to emphasize that sometimes feels weird depending on how you think about it. Well, any last questions, folks, about these so far? Okay, I think these are pretty tough concept questions in a certain sense. So that's why we'll have the opportunity to take a look at them a second time in the chapter 14 homework. This will be a good one to come back to as a guide. But don't hesitate to reach out to if you find out you're answering some concept questions that come out to be a little bit vague in the homework. I'll always be happy to help. Last one says, when we give a practical conclusion, we state the confidence level. However, we do not consider the confidence level as being the probability that mu is an element inside the interval from A to B. And we recall why that is. Kind of weird in a certain sense. We often want to say we have a 95% probability mu is between these two values, but it turns out to be false in a weird way. Like this one deserves a really carefully typed out statement. So let's say it's right here. Because again, it's pretty weird. We've mentioned it before, but these are those kind of ideas where you have to think about it a lot before it really kind of settles in. We make the right connections in our mind. We don't have a 95% chance, if it was a 95% confidence interval, that mu is in AB. Let's say it this way. If C is 0.95, so a 95% confidence interval, then the probability that the method of select a simple random sample, size n, compute the confidence interval. So if confidence is at 0.95, then the probability of doing this let me say this in a different way, the probability that the method of doing this and this is the part that my brain is struggling to connect, and then producing the interval from A to B, like stated at the top of this problem, has a 95% success rate. So what's being conveyed by this is if someone else selects a simple random sample at the same size n as we did, sample size 16, they will absolutely have a different interval. They have different fish. There's no reason for the sample mean to be the same, and the sample mean determines the center of that interval. So replicate this 100 times at 95% confidence, you expect 100 different intervals, some of them very different. But this whole procedure has a 95% success rate, means 95 of those 100 intervals will contain the unknown parameter, despite the parameter itself is unknown. So this method of producing the interval succeeds in capturing an unknown quantity, population mean mu, 95% of the time. So we don't have a probability that mu is in AB. It either is or it isn't, but we have a probability associated with the entire method of collecting data and computing the interval itself. This is the really tough one, but really the big takeaway from this is in our conclusions, we must say confidence when we say the confidence value instead of probability. Well, that's the end of all the concept questions on that one. Any last questions, comments, or additions so far on thinking about these confidence intervals? Okay, well, as RStudio kind of indicates, it's really not too hard to calculate the confidence interval. It's really pretty fast. But the one interval we're doing, sometimes called the Z interval, that's actually not even programmed into RStudio. RStudio doesn't want to have anything to do with it. I think that's kind of interesting. So again, think of chapter 14 as it's just a first look into inference. It's called Introduction to Inference for a really big reason before we get into chapter 17. What we'll be doing next on Thursday is turning it all around and taking a first look into hypothesis testing, much like our first look into confidence intervals. So we'll get the feel for what do we mean by a hypothesis when we do a hypothesis test. We'll state some really simple ones just to get going. And then here's the full procedure. We'll fill out a little bit with some R syntax on how to calculate the p-values. Finally, we'll do another complete analysis. These are pretty long notes in chapter 14. Then another set of fast concept questions right after. Well, the exciting thing is we're returning, no, we're not. Well, we'll return to one of the problems from the start of the course. I think it's this one, and give it an analysis at some point. But it looks like this is just another look at the problem at the start of the course. Well, this is where we'll end today. Next class, we'll look into hypothesis testing. Have a great night, folks. If you do have any questions, keep in mind Tuesdays are good days for me because I don't have a 7:30 class, so I'm happy to help out. Have a great night, folks. I'll see you all in Thursday's class. Oh, and if I haven't returned your exam, I do have them down here. Feel free as well, if you'd like your exam scanned and returned to you, I'm happy to make that happen. Thanks, you too.
I think the only way you could ever get all the fish is, well, you would never be able to do it in that particular species because of such a wide range of size.
They really travel.
If you were, I think the only species would be if you were to go to, say, the Devil's Hole in Nevada and collect all those pupfish, but that would kind of defeat the purpose.
Right. They didn't want to have exposure to cesium. Yeah.
Sense. or whatever you were studying them for, since if you're studying the fish, I assume you have some plan for them.
Yeah, true.
Have an excellent, day.
Thanks, you too.